How does the R value of a material affect the cooling or heating load of a building? What is the basic equation for the conduction of heat through building construction such as walls and windows? What happens to the total heat when the temperature difference between the outdoors and indoors increases or the R value is doubled? We're often asked to add air conditioning to a space that has never had air conditioning before. One of the factors that needs to be considered is the components of the building shell that will contain the conditioned air. This would be the walls, windows, roof, and floors over unconditioned spaces. Here is the equation for the transmission of heat through building components by conductance. This doesn't consider other heat gain or loss methods such as infiltration, ventilation, lights, people, plug, or solar loads. This also just looks at single components and not the full wall assembly, including interior and exterior air films. Q equals A times U times delta T, where Q equals total BTUs per hour, A equals area, square feet of wall or window, U equals building assembly's overall heat transfer coefficient, BTUs per hour per square foot per degree Fahrenheit. Delta T equals difference in outside and inside design temperatures. Here are a couple of examples of how different construction materials stand up against preventing heat transfer by conductance. This could either be heat coming into the building or heat going out of the building. We'll start with a wall that has 1,000 square feet and a design indoor temperature of 75 degrees Fahrenheit and an outside design temperature of 90 degrees Fahrenheit. This equates to a 15 degree Fahrenheit delta T. So far we have the area of the wall and the delta T. The missing factor is the U value, which is determined by adding up all the resistance of the components of the wall and taking the inverse value. Here are 4 different building construction components and their R values. 1/8 inch clear glass, R equals 0.76. 1/2 inch plywood, Douglas fir, R equals 0.79. 8 inch lightweight concrete block, R value equals 2.33. 3.5 inch R11 insulation, R value equals 11. We performed the heat transfer equation on each of these building components, starting with the 1/8 inch clear glass and a U value of 1.32, we get the following. 1,000 square feet of glass times 1.32 U factor times 15 degree delta T equals 19,800 BTUs per hour, or 1.65 tons of cooling required for the heat gain through conductance. Obviously, there are glass windows with much better U values, but our purpose is to show you how the R value and inversely the U value affects heat transfer. As you can see, if we built the wall with just plywood, we would do a little better with a heat gain of 18,975 BTUs per hour or 1.58 tons. Using 8 inch lightweight concrete blocks helps considerably by reducing our total heat load in thirds. The greatest effect comes when we add R11 insulation to the wall, which in this case looks like this. 1,000 square feet of R11 insulated wall times 0.09 U factor times 15 degrees delta T equals 1,350 BTUs per hour or 0.11 tons of cooling. This is a huge reduction in the amount of heat that can transfer from outdoors to indoors. This shows the importance of properly insulating the shell of a building. This chart shows that the greater the R value or resistance of the construction component, the smaller the U value will be. The smaller the U value, the smaller the heat transfer rate. This is why energy codes mandate a certain R value for insulation in walls and roofs. If the outdoor temperature increased to 105 degrees Fahrenheit, this would double the delta T in our equation, which would double the heat gain through our building components. This is one of the reasons why the temperature outdoors makes a difference in the energy consumption of the building for comfort, cooling, or heating. Most energy codes have standard requirements for the total allowable transmission factor that can be used to construct a wall or roof for a space that is air conditioned. It wouldn't make sense to allow the heating or cooling of a space built with paper walls, as heat would easily enter or escape the space, requiring enormous amounts of energy to condition. A high-quality wall, floor, window, or roof assembly is essential to prevent heat gain or loss in buildings, ensuring energy efficiency and maintaining a comfortable indoor environment by effectively insulating against external temperature fluctuations. If you like that video, please give it a thumbs up and subscribe to our channel. Thank you.